Hi guys. So I wanted to really build on a lot of what the previous talks have had, I think focusing on the importance of posteriors and how we kind of care about predicting our target outputs in a statistically reliable way. I want to tell you about two very different features of Bayesian deep learning, which I think are really useful. The context is that I'm working with Galaxy Zoo, a third-year PhD student at Oxford. We're trying to classify galaxies. So Galaxy Zoo is all about, it's a crowdsourcing website if you haven't heard of it, galaxyzoo.org. We have an app, check it out. We ask people, we show people a picture of a galaxy, and we lead them down a kind of decision tree of simple questions like, is it smooth, is it featured? And as we ask questions, we gather answers, we aggregate them up, and we provide those to researchers. If you're a cosmologist, like Neil yesterday, if you're a weak lensing person, then my entire field is your error term. So maybe you don't care. But take it on faith that a lot of the astronomy community cares about galaxies, and that how they look is one of the most fundamental things you can measure. And Galaxy Zoo is probably the main way that researchers find that out. Here are the projects that Galaxy Zoo has been running for the last few years, starting with Galaxy Zoo 2 in about 2014, through to Galaxy Zoo Decals now, which is the project that I run. Pretty soon, we're going to have LSST and Euclid coming online. Once LSST comes online, if we want to classify every galaxy in LSST with Galaxy Zoo, we'll need to handle this many galaxies. And if we want to do the same for Euclid, we'll have to handle this many. Challenging. So clearly, we have to scale Galaxy Zoo, but we also have to make sure we scale it right. And I think to do that, the key is Bayesian convolutional neural networks. But driven by the science at Galaxy Zoo, I've been adding kind of two twists to that. The first twist is all about label uncertainty, right? So predicting good posteriors is very important, but for Galaxy Zoo, we also have very uncertain labels, right? Because some galaxies are inherently ambiguous, the aleatoric uncertainty we talked about. Some volunteers have different skill levels. And most fundamentally, because of that decision tree we walk people down, all the interesting questions in Galaxy Zoo only get asked of a few people. So some galaxies will have 40 responses, some will only have 4. And all the previous work has either taken the average response to be true, which is kind of living dangerously. They have only focused on the first question, which doesn't let us answer all those interesting parts. Or they've thrown away all the galaxies that only have a few responses, which is most of them. Right? So to do good science, we have to be able to handle this label uncertainty. This is what I've been working on. So we'd like to have a CNN that can, first of all, predict posteriors. So as we've been talking about, and here's some examples of that. So each row is a galaxy. It will have a bar or not. We ask our model, does this galaxy have a bar? We're going to do that by really a careful choice of our loss function at this point. So we recognize that asking n volunteers, does this galaxy have a bar, and getting k responses back, yes it does, is a lot like having n trials and k successes. So we're going to model our volunteers as sort of binomially distributed. That gives us then a likelihood for given that we've asked n people and had k responses back, what is then the reasonable typical probabilities that a volunteer will say yes or no. And that's going to be the target for our network to predict. And we'll just directly minimize that analytic log likelihood. So we have a probabilistic model in that sense, but it's not yet Bayesian, right? Because in the Bayesian framework, the weights in the model are also random variables to be marginalized over. And we can do that, as we talked about a lot before, to some degree with dropout. So if you take these sort of single predictions of that typical response probability before, marginalize over the different weights the network can have, and that's kind of what these black traces are. Once you marginalize, you get down to the sort of green aggregate posterior, if you like, and that turns out to be, well, first of all, it can now take any shape, which is nice, or any smooth shape, and second of all, it turns out to be much better calibrated. So to show the calibration, this is kind of just a coverage plot in a weird format. So on the x-axis is like how wrong how wrong are you allowed to be? And on the y-axis, how often do you expect to be that wrong? And the dashed line would be a perfectly calibrated model. In yellow is the model without dropout, just a probabilistic model. And in blue is the model with dropout. So it's much less overconfident. But note, though, that it's still somewhat overconfident. And this goes back to that kind of panel discussion that dropout is a useful but imperfect approximation. So do bear that in mind when you use it. Just to kind of hammer home the idea that uncertainty is not like just a philosophical question. It's a really important scientific thing to bear in mind. I did a bit of a test. So here's a sort of science question. How many bars are there in a sample of galaxies? Right, so we've had an expert, or took an expert catalog of labeled galaxies to be bars or not bars. We said, all right, how many bars do volunteers think there are? You know, allowing some mapping between volunteer skill and expert skill that we can work out straightforwardly. And they got it about right. Then we took a standard CNN, the most recent automated machine learning catalog of bars, and said how many bars, if you add up the so-called probabilities, how many do you get? And you way overestimate, right? But when you use the sort of Bayesian CNN method with the binomial loss function, with the dropout, you get back to bang on the right answer. So this has quite a big impact then on, as a scientist, asking important questions. You will get the wrong answers if you don't use calibrated probabilities. The second thing that I kind of want to focus on is, all right, we have our clever BCNN, we have our reasonably good, certainly somewhat calibrated uncertainties, and that's hopefully useful to the scientists we work with. But what else can we do with those? And I want to remind you guys a little bit. I don't have a mic. Oh, well, I'll stay here. I want to remind you guys about that context where the vast majority of galaxies going forward, because of the sheer scale of the surveys coming online, cannot be classified even with crowdsourcing. We have something like 2 million volunteers over the history of Galaxy Zoo over about a decade. Or I don't know if that number is quite right, but you know, it's in the order million. How many could they reasonably do is going to be a very small fraction of all the galaxies we need to classify. So in that context, the most important thing is to build the best possible model. And to do that, our model should be able to ask, hey, this galaxy would be the best possible galaxy to label. It would be most informative to me. Can you go and label this one? And that galaxy, well, it's kind of a boring blob. You know, I can already do a good job at that. Let's focus our labeling effort on the galaxies that really matter. What principle can we use then to choose which those galaxies are? So this is not going to be the next two, this talk is my work, the next two slides are the part that's not. This is not my derivation, but I think it's really interesting, and I kind of want to share it with you guys. So there's two things that you really want to know. One is the mutual information, which is like how much information X carries about Y. And that formula you really can't argue with. That's like straight out of Claude Shannon. The second formula, we need to have some idea of how much information do we gain when we label a subject about our model parameters. And this one is a bit more of a choice, but quite a reasonable thing to do is to look at the change in the entropy over my model parameters before and after I've labeled my subject, my galaxy in this case. And the really important thing to note is that the mutual information is symmetric. That's going to be super important. So we'd love to then just say, calculate the information gain for every subject and pick the ones with the highest gain. But unfortunately, we don't know what that is because we don't know the distribution of our weights, as Tom talked about at length. And we definitely don't know the entropy over the distribution of our weights. But what we can do is we can recognize that we can rewrite this as the mutual information between our model parameters and our labels, and then by symmetry flip it around and expand it back out again. And it turns out that when you rephrase it that way, our information gain is now expressed in terms of things that we know because it's after the probability of Y given X in our data set. Really, these are then our posteriors that we have worked really hard to get. So now we can calculate not quite exactly, but very close what that is. The close part is that we still have this expectation over weights, and we'll approximate that with dropout. So the intuition here is that we're picking galaxies where each model is confident, so the the entropy of the predictions of a particular model is small, but once you marginalize over the models, those green posteriors, they disagree, right? And I think it's quite intuitive that where our models disagree, those will be the ones that we really ought to label. And that's kind of in contrast to uncertainty sampling that Emily talked about, for example, yesterday, which is really just the right-hand term of this, right? And that's kind of tricky because in the context of aleatoric uncertainty, some galaxies are just ambiguous, and it doesn't help to get more labels for them. But if you only do uncertainty sampling, you'll just keep hitting those ambiguous galaxies, and you will at some point not be able to improve the model. It'll actually be a pathological case. So it's really important to break that out into those two terms. So this is what I've been applying for Galaxy Zoo. And it's only possible because we have those posteriors. And if we didn't do this in the Bayesian context, we couldn't calculate any of this. Here's what happens, very briefly. So on the x-axis is sort of time, or more training samples, if you like, as we add more galaxies and continue training our models. On the y-axis is our sort of error. And it turns out that you can get a model to a certain level of performance, something like twice as fast if you do this active sampling than if you just pick randomly. So for Galaxy Zoo, that's a big deal because it means we get to give you galaxy classifications back for new surveys twice as fast. It's kind of interesting to me to look at what these galaxies are. So on the left side, we have the galaxies which are high mutual information, galaxies that are informative to the model. And on my hand side, we have galaxies that the model didn't find informative. And I think it matches our intuition really well. So we have informative galaxies which are interesting, which are diverse, which are complicated. And we have not informative galaxies which are basically Gaussian blobs that probably you could do a good job classifying just by doing a fit. Basically, you don't really need a clever CNN. So that's kind of neat. And the effect of this is so strong that it turns out most galaxies are smooth for the particular surveys we're working with. By far, most of them are in the smooth section. But the model so strongly prefers galaxies which are interesting, quote unquote, that it totally flattens out that skew in the data set to the degree that it even slightly prefers featured ones. Question for you guys. So if instead we train a model to predict if a galaxy has a bar or not, these kind of linear features in the middle, these are the galaxies it finds informative or not. Can anybody tell me what the difference is? Seeing, yes. Well, essentially, yes. So resolution, right, proportional to seeing. So the galaxies which are informative, you actually can see if they have a bar or not, right? And therefore labeling them helps. Whereas the galaxies which are not informative are kind of blurry in the middle, and it's not clear what information you'd gain from labeling them. And I didn't expect this. I didn't tell the model to do this. It just followed from the mathematics that those were sensible galaxies to pick. We can make that a little bit more quantitative to sort of proxy it with redshift, right? Because our ability to resolve the center of the galaxies will depend mostly on how far away they are. And the model strongly prefers galaxies which are at somewhat closer redshifts where the bars are in fact resolved. So I'm really happy to say that as of a few months ago, this is live on Galaxy Zoo. So if you go to galaxyzoo.org, this is what you'll see. And if you choose our sort of enhanced version, then which most people do, about 95% of people do, they like the word enhanced, I guess, then the galaxies you see will be chosen for you by a Bayesian convolutional neural network using the mutual information to choose which galaxies it will find helpful. I'm really curious to see how this pans out. In principle, we should be able to crank through surveys in weeks instead of years, but by optimizing the use of our volunteers. Now, we do still make sure for now that all galaxies are seen by at least a few volunteers in case there's an alien or something in them, right? People are really good at finding the weird and the unusual. That's often called the scientific gold dust. And I think finding those is a separate and very fascinating machine learning problem, how you find the weird anomalies that relates to active learning in the sense that we are also trying to find the interesting things. So hopefully these are complementary. But for now, we do make sure galaxies are seen by a few people. I'm coming to kind of the last year of my PhD, so I'm running out of time a bit to work more on this. But I'm really excited to try some more sophisticated approximations to the weight posteriors, and also some really simple ones, like can we just train 100 models? It's not that big of a deal anymore, and see what happens, right? There's a point at which being robust is better than being clever. So I hope that this will be useful for galaxy astronomers, and I think that it's generalizable enough to perhaps help you guys in your research as well. Thanks very much.
Question for Mike?
Thanks. It was really interesting. Do you think this I was just thinking of the example where you had the lower resolution and the higher resolution one. Do you think this framework generally allows you to deal better with more heterogeneous data? Yeah. For example, that it doesn't go crazy when it sees something with different noise and different surveys.
Absolutely. I talked to quite a few industry guys who are curious about, how do we label our, very large amounts of terrain or autonomous driving data or something like this, right? It's a similar problem. And the truth is that the CS guys are very focused on their homogeneous, their MNIST, their CFAR, their ImageNet data sets, which are like deliberately homogenized to make it a good test problem. But actually most interesting practical problems are extremely heterogeneous. There'll be a few curious, interesting things. There'll be a really long bulk of like the boring, empty pictures, right? And astronomy, where most, a lot of our galaxies are just blobs, but a few of them are super interesting. So I think data which is heterogeneous is the perfect application for this, and also data which is expensive to label, either in terms of like volunteer time, which is limited, or outside of astronomy, stuff like privacy, right? You can only collect so many medical scans and this kind of thing. So those are the data sets that would be interesting to apply this. I want to say before Emilis answers that this whole research topic was inspired by your UK NAM 2018 talk, where I was in the audience and I was like, wow, we should totally do this for Galaxy Zoo. But I added the deep.
Thank you. Actually, thanks for the talk. I knew this work and it's really nice. I have so all of these volunteers, they do separating this stuff. And then you probably have some experienced astronomers who are going to look through what they do. So do you do that, like some kind of active learning also in the phase to select what the experts are going to look at? Because let me contextualize what I'm thinking is that for the weird stuff, for example, I would naively think that a professional astronomer would be more likely to, looking at some images, identify some scientifically interesting weirdos. Yeah. But then you would need a second layer of active learning on top of what the volunteers have.
Would you be doing that in order to find the weird stuff primarily? Yeah, so I mean, the short answer is we don't, probably we should. I think a sensible strategy though would be, as opposed to another layer of active learning, I think that for anomaly detection, you can probably do a better job with a more targeted at the weirdos kind of a system. I think that there's really interesting work, I mean, your presentation yesterday, for example, right, where you can, I think the key is what's weird to you is not necessarily weird to me, right? So we have to, I think it needs to be more of a recommendation system approach where astronomers will be looking for something weird, and we can find nearest neighbors in high dimensions, and we can listen to what they say, yes, it's interesting, no, it's not, and then serve more of those, I think is the way forward for this.
All right, another quick question? Well, if not, let's thank Mike again.